Okay, these are the notes for limits, first day of limits. So our unit 4, our part 1 was rationals and our part 2 is limits. I'm not going to really talk through this much, you all. If you weren't in class, important that you watch the video that I posted for your intro to limits. And then biggest thing we talked about here, and sorry, this quality is not the best, but this right here, when you see that little negative right there means that it's approaching x, whatever the x value is. So in this case, it's a, right? So approaching a from the left side, left of a. And then if you see the little plus here, then that means it's approaching a from the right side of a. So it's not necessarily positive and negative. It could be in any quadrant, but it just means from the left of that value and from the right of that value, the right side of a. Okay, and then if those two are equal, then the limit exists at that point. So you should have seen this in the video. Like, for example, I don't know if I have any like polynomial curve, let's say, and I call this a right here. As I'm coming to that point from the left side, I'm hitting right there. And as I'm coming to that point from the right side, I'm also hitting right there. So I could say that that limit as x approaches a of f of x, let's just say this guy is f of x, would exist. Okay, so the left and the right side limit have to be the same value. In other words, it has to be a continuous function at that point. It has to be continuous at the a value to exist. Okay, so hopefully that is clear as mud on that part. This next part is just going into a little more detail about one-sided limits, and I have this paper posted with my notes from class. But basically, right, if we're looking, you can read all these on your own, but if we're looking at this graph right here, you should be able to notice that at value C, so as the limit approaches C, this is discontinuous. So because this right side limit and left side limit would not be at the same value, AKA the graph has a break in it, then this limit as x approaches C, and I think the graph we're calling, what are we calling this one? Maybe let's just call it f of x again, I guess. It doesn't really have a name here, but of f of x, would be DNE, does not exist. So it can be defined in terms of the left side would be at L and the right side would be at M as far as the limit, but the limit overall does not exist because those 2 points are not the same. It's not a continuous graph, okay? The last thing that this is showing here is that when I have an asymptote, most of the time when you have an asymptote, y'all, you have something on both sides when we're talking about rational functions. But like this one right here, this would like be maybe a part of a rational function that's restricted, or it could be like a logarithmic graph that's been reflected, right? So when it has an asymptote and you only have a value on one side of that asymptote, then we actually say that the limit does not exist here. Okay, it has to be on both sides, the limit can be defined. So if I had a little portion down here, then that would be fine. I would say this one's going to infinity, this one would be going to negative infinity if my curve is going down, but then the limit wouldn't exist. But when there is only a partial function on one side of an asymptote, then the total limit does not exist here, okay? So we have to be able to have a left and a right-hand limit for the limit to exist. Okay. There are 3 ways to evaluate limits. We're gonna look at all 3 right now, from a graph, from a table, and from an equation using algebra, okay? All right, so let's dive into that. And again, sorry for my quality here on my paper. It's not the best. Let me see if I can zoom in a little. Okay. All right, so, and you should be hopefully looking at this on your own paper too. I'm gonna try to use a little darker color so we can see. So if we're looking at this graph here, I can see I have a piecewise function, right? A parabola, and then I have a, maybe a part of a line or an absolute value function here. So, and I see I definitely have some removable discontinuity happening there. I can see I have a point of discontinuity at x equals 2. So kind of look at the graph before you start and get a gauge of what we're dealing with. Okay, remember really quick, I'm gonna have you write this down. Limits describe graph behavior. So a limit may be defined when a point is undefined. Let me say that one more time. A limit may exist where a point is undefined, and that's okay, because it's talking about the graph behavior rather than the actual value of that point. So we'll look at that right now, okay? So as I'm looking at g of x, and I'm approaching -2, so as x approaches -2 from the right side, okay? So here's -2. I can see that I have a hole right there at x equals -2. From the right side, I need to get down to this part so that I can come towards -2. And then I'm just actually gonna name that y value right there. So that's -1. Okay, so as I approach -2 from the right, I'm trying to get to y equals -1. Even though that's undefined, I can tell my graph passes through where that would be. So I still say the limit there is -1. As it approaches 2 from the left side, that would be as I'm going along my graph, I'm on the left side of -2, I'm coming towards -2, and I'm still at that -1. So again, because it's a continuous graph, the left and the right-hand limit should match at that point. And then because those are equal to each other, then I can just say the limit as x approaches -2 is -1, okay? The next one, if I'm looking at it, as x approaches 0. So really similar. At 0, which is right here, I can see that my graph is continuous. So whether I'm coming from the right and getting to that -1 or from the left and also getting to that -1, my limit at 0 is going to be -1 because these two values match, okay? Now let's do the point where it's discontinuous. Okay, so if I'm looking at my graph at 2 here, and I can see I have a point of discontinuity, right? I have a point up here and then it jumps to down here. So as I'm coming from the right of 2, boom, I'm trying to hit 6. Even though there's a hole, once again, even though there's a removable discontinuity, that's okay because my graph is still heading to that point. And then because it's describing my graph behavior, not my defined point. And then the limit as x approaches 2 from the left side, as I'm coming from the left and I go to 2, I'm now at 3. So as soon as I see that these two values do not match when I'm coming from the right and the left of that value of x at 2, then I would say the limit does not exist. And if we had looked at our graph ahead of time, we should have kind of already anticipated that since we have that jump discontinuity right there, okay? All right, so again, reminding you that this limits describe graph behavior versus if I'm saying, what is f of 2? Then I'm evaluating that point, and f of 2 would be the one that has the closed circle. So that would be 3, okay? F of 2 at 6 would not exist, right? Or be undefined, I should say, be undefined. Okay, so that's how you do from a graph. Limits from a table, as I'm looking at this. I want you to just notice, I got a 3 in the middle here. And then these values, hopefully you see, are to the left of 3. And I'm getting super close to 3, 2.9, then 2.99, then 2.999. I'm almost 3, right? I could keep going, 2.99999999999 forever. And I can see that these values look like they're getting closer and closer to maybe 6.2 approximately. And then as I go from the right, so these values are to the right of 3 because they're a little bit bigger than 3, a little greater than 3. And I can see also that I'm going 5.9, 6.14, 6.198. It looks like I'm also approaching 6.2. So we're gonna write two limits that correspond to that, okay? And I'm gonna do it down here so you can see it a little bit better. So the left side values here, the limit as x approaches 3 from the left of this function is h of x this time. Make sure you always put your function rule here. Otherwise, you cannot just have a limit floating without a function next to it. Equals 6.2 approximately, okay? And then my right-hand limit, so this is letter A here, would be my limit as x approaches 3 from the right of h of x is also approximately 6.2. So because they're approaching that same value there, then I could say for letter B, yes, the limit as x approaches 3 of h of x exists. Because the limit as x approaches 3 from the left of h of x equals the limit as x approaches 3 from the right of h of x. So because that is continuous at that point, they're both approaching the same value, then I would say the limit as x approaches 3 of h of x does exist. Letter C, what would be the value of h of 3? So this is kind of what I was talking about up here. So now not the limit, but the actual value. So looking at this, we could assume, you all, that it's 6.2. But because we're talking about limits, it also could be a whole, just like it was on this one, right? So if it's a whole, then it actually would be undefined. So, right, so I'm gonna say h of 3 could be 6.2 if the function does not have a removable discontinuity. Continuity, or a whole, right, at 3, 6.2. So we're assuming that it doesn't, but we can't be totally sure, right? So h of 3 could be 6.2 as long as that function does not have a removable discontinuity at that point, okay? That's our table. And then from an equation, this part uses a lot of stuff from previous algebra classes. So you have to really put your brain to work on these. And we will practice these next class. But this first one, first I told the students that were in class with me, you want to first step, always, first check if you can substitute and evaluate with no issue. Always check that first, because before you do a bunch of work and like factoring and everything, you might just be able to directly plug the number in and then you're done, okay? But if we can't, we have to maybe manipulate. So let's try letter A here. So can I just directly plug in 1? Let's check. So x approaches 1, and I'm just gonna try plugging 1 in here and see what happens. Ooh, yeah, looks good so far, right? Because I'm not gonna get 0 in the denominator, so that feels good. Make sure you recopy limit every time. And then, let's see, what would I get here? This would be, let me go ahead and stick like f of x so I can get my answer. So 1 squared is 1 plus 2 over 2, so 3 over 2, and that would be your answer there, okay? So that is how you would write that answer. So I'm gonna put an equal sign, 3f's. So that one's super easy, direct substitution and done, okay? Now, when we get to letter B, we can see that if we substitute, 1 minus 1 is gonna give us 0, boo, right? So that's not gonna work. But I do see that I have an x squared minus 1 in the top. So this one's gonna be an example where you're gonna factor first. Okay, so that's gonna be your second thing. If you can't directly sub, check and see if you can factor something and maybe cross something out. So I'm gonna tackle letter B down here. So limit as x approaches 1, I'm gonna rewrite it with my difference of squares on top. And then I have x minus 1 on the bottom. I can cross out my x minus 1s. And so I'm going to do a limit as x approaches 1 of x plus 1. And then if I substitute 1 in right there, hopefully you can see that's just going to be 2. Right? When I plug it in, 1 plus 1 is 2. So you're done. And that's fine for the answer. Or we can go back to that original, right? X squared minus 1 over x minus 1 and just say equals 2. Okay, next one. We cannot directly substitute. Square root of 1 is 1, 1 minus 1, 0, boo. That's going to give us a 0 in the denominator, thus making it undefined, right? We cannot divide by 0. I also don't see anything I can factor. So this one is going to be an example where we have to rationalize to get rid of that radical. To remove the radical from the denominator, okay? Most of the time you only have to do this if the radical's in the denominator, but occasionally you might have to do it in the numerator. But biggest thing, we don't want 0 in the denominator, right? So that's why we're gonna have to do this. And you may not quite remember this, but that's okay. We're gonna go over it right now. So limit as x approaches 1, x minus 1 on top, I have square root of x minus 1, not in the square root on the bottom. And then to rationalize, I want to use the conjugate of this. Use conjugate to rationalize. So remember conjugate, y'all. We did them in the last unit when we were finding complex roots. Yeah, so when we were finding complex roots, remember we had like 3 plus 2i, and then we would say, oh, okay, 3 minus 2i would also be a root because that's the conjugate, and they come in pairs. So a conjugate, remember, just changes the second value sign. So it's going to be square root of x plus 1. And I just have to make sure whatever I do to the bottom, I do to the top, so that it's kind of like I've done nothing. I'm just multiplying by 1. And then I'm going to simplify that, okay? So when I have an equal sign like this, I have to keep writing limit, y'all, or it's not correct. So just be careful there until you've actually evaluated. You got to keep that limit going. Okay, so if I multiply this top part, I get square root of x, x times square root of x. Let's write it like that. And then I can see I'm going to have a plus x, a minus root x, and a negative 1 times 1 minus 1. So unfortunately, nothing can combine there, but that's okay. We're going to just leave that for now. Our goal is to be able to substitute the 1 in and evaluate this limit, okay? The bottom, when I multiply, let me go ahead and put this in parentheses and this in parentheses so you know that why I did that. So if I multiply this, this is now a difference of squares, right? So square root of x times square root of x is just going to be x. And this are going to cancel. And then negative 1 times 1 is negative 1. So now I can see that, unfortunately, it's not going to cancel. And I actually made this, I just went too far in class. If I look back to right here, if I hadn't multiplied these out, you all, do you see that I have an x minus 1 here, and I also have an x minus 1 in the bottom? So actually, that's what I'm going to do. So I'm going to just take a beat and go back and make sure that I actually don't multiply those out, because I was able to cancel if I hadn't, okay? So now, boom, boom, I can get rid of that x minus 1, and I can evaluate. So now I have nothing in the denominator except 1, and I can plug this 1 in. Square root of 1 is 1, and 1 plus 1 is 2. So this is going to be 2 for my answer. Okay, so here equals 2. Done. Whew. All right, let's do 3 more. Hang in there with me. Letter D. All right, we got a lot going on letter D. X minus 1, that's fine. I'd get 0 in the numerator. That would be A-okay. When I plug in 1 in the bottom, 1 plus 1 is 2, 2 squared is 4, and 4 minus 4 is 0. Uh-oh, that's going to make it undefined. So I am going to have to manipulate this denominator. So what I would recommend on this one is it's going to be factor like letter B, but we first have to unfactor. So first you want to multiply and combine, and then factor. Okay, so just think we want to have like all one thing that we can work with down here on the bottom. So let me go ahead and copy this, limit as x approaches 1 again. And then my numerator is going to stay x minus 1. I'm just going to stick it in parentheses, make it a little easier for my brain. And then x plus 1 quantity squared. When I multiply that out, I get x squared plus 2x plus 1. And then minus 4. And then I want to do my limit again because I haven't evaluated yet, so I want to keep writing it. X minus 1. I can combine these together, right? And that would be 1 minus 4, which is negative 3. And then let me just write it under here. Minus 3. Okay, this is the part we want to factor. Hopefully one of the factors is x minus 1, so I can cancel that out because the 1 minus 1 is what's messing me up here, right? I don't want to get 0 down there. But does this factor into x minus 1 times something? It does. So x minus 1, x plus 3. That's going to give me that, right? Product sum is product's negative 3. Sum is 2. So 3 and negative 1 would do that for me. And then I can cross those out. And then I can say the limit as x approaches 1. And it's 1 over x plus 3, and then I can evaluate, and that would be 1 over 4. Done. Okay, good. All right, letter E. If I look at it, this is a complex fraction, so we need to get rid of the complex fraction. Okay, so let me write that one on the back here. Letter E. So limit, again, as x approaches 1. X minus 1 over 1 over x minus 1. I could graph all of these too, y'all, and check them, but I do want you to be able to manipulate them using algebra. This is really good for our brains to like practice all the algebra we know. Okay. First, to get rid of the complex fraction, I have to like combine these, right? Combine into one fraction. Okay, so I'm gonna make this x over x so that I can go 1 minus x over x. Get that common denominator, x minus 1. And then remember, this is just division. So, oops, I forgot to write my limit, because I haven't evaluated yet, so be really careful. Limit as x approaches 1. Okay, x minus 1 is going to stay where it is. Let me write it a little bit more normal because I'm going to flip and multiply, right? When I divide fractions, remember you can just multiply by the reciprocal. And then hopefully you're seeing 1 minus x could be x minus 1 if I take out the negative. So x minus 1, right? Because that would still be negative x, and that would still be positive 1. Okay, so just took the negative out. And then I can see that, oh, wow, look, I can cross those out because I could just pretend like that's in parentheses. And then I have just negative x, right? So then I have limit as x approaches 1 of negative x. And that's going to be negative 1. Okay, so that's complex fraction example. And then the very last one is actually the easiest. Because if I look at it, 1 over x minus 1, there's like nothing I can do to that. Even if I multiplied by x plus 1, it's not really gonna help me because I can't cancel anything out. I'm still gonna have that x minus 1 there. Why is that, y'all? Think about this one practically. This is just our parent function 1 over x shifted to the left one. So that is going to be a non-removable discontinuity. This has a vertical asymptote at x equals 1. So therefore, the limit does not exist. So you would say equals d in e for this guy. Okay? Thanks.